All right, guys. So I don't know if you guys have been taking notes, right? But you should have been taking some notes pertaining to this that is on the screen, right? All of what we have been going through so far, right? I think I had shown you that this is the equation that we want to prove, right? We need to reach to this equation. And this equation is just an equation that we can simply use whenever we're trying to find the pressure of something and all of that, right? So we're going to see where we left off here. I think the last thing that we left off was to say that let's imagine that there are several particles, right? So at first we started out by looking at one particle, and we said that that particle is going to collide with the face of the wall, right? And because it's going to have what we call elastic collision, then you would expect that the same momentum that it had going towards the wall is the same momentum that it's going to have when it bounces back. So we have been using all that information coming along the line, and we're at a junction where we're now considering the overall pressure on several particles that are colliding with one particular face of the wall. So if we're looking at this, let's imagine that this is the box. Let's imagine that this is the box. Give me a second here. Right? Let's imagine that this is the box. Right? And we have a particle that is colliding with this box. Clearly, there are several other particles that will be colliding with the box as well, which means that they're going to have a particular velocity. So what we did just now was to find the average velocity, right, of the particles. And how we go about doing that is by adding up all of the velocities and dividing it by, well, this right here is basically the average velocity squared, right? Which is just telling us that I'm adding up all of my velocities and then dividing by the number of particles that are there. But because I know the number of particles that are present, I have to factor in that number right here, which we're going to call at n. So this n basically speaks to the number of particles that would essentially be colliding in the entire cube, so to speak. So we're at this point where we say that P is equal to m divided by v times n times the average velocity squared, right? I'm wondering if I said that correctly just now. Let me see if I said that correctly. We that n shouldn't have been there as yet. That n that I put there shouldn't have been there as yet. What's going on for this thing, man? Yes. So that n that I put there in this formula, it shouldn't have been there as yet, right? Should it have been there? Let me check. It's gonna eventually reach there, but I kind of jump ahead of myself a little bit. So let me just that kind of robot. But at the end of the day, we soon reach to this point. Let's give me a second here. So this is the line that we want to focus on. We want to focus on this line, right? So here's our velocities, and we are going to find the average of that. When you're trying to find the average of something, you would add them up and divide by the number of them that are present. So when we go over here, right, the average speed square, or in some regards you hear us call it the mean square speed, right? This is how we really find the mean square speed, by just adding up the individual speeds of the particles, dividing by the number of molecules or particles that are present, right? And that is how we get this thing what we call the average velocity squared, or we can say the mean square speed, right? Which we denote it as such. So these things that are in front of it, it has to be there, guys. So don't neglect this, because this speaks to the fact that we're talking about the mean square speed, or we call it the average speed squared, or something of that nature, right? So it has to be there, and this, as we said, it means that. So when we go back to the equation just now, right, that says P is equal to M over V times all of this thing. We're going to replace all of this U1 squared plus U2 squared plus UN squared with this that you're seeing down here that says N times the mean square speed, right? So that would account for just only the particles that are colliding along one aspect of the cube, right? Now, what we have to understand is that when the collision is taking place, right, there are three main axes that a typical three-dimensional object will have. You have the x-axis, the y-axis, and the z-axis. What we looked at just now was finding the total pressure along the x-axis, right? That was the total pressure along the x-axis. Now we need to consider what is happening along the y-axis and the z-axis, right? What we have to understand here, guys, is that the pressure that is exerted on the x-axis is going to be equal to the pressure exerted on the y-axis, and also going to be equal to the pressure exerted on the z-axis. All right? Now, it says here, since the mean square speed, right, on the x-axis is equal to, because what you have to understand, if I were to take this equation, if I take all of this right here, right, and pretty much eliminate the things that are common, then I would end up with this equation that says therefore, right? Because the volume is constant, the number of molecules is constant, the mass of the molecule is constant. The only difference is that we're going to have here is that the speed on this side is going to be different for the most part, right? It's going to be different along the x-axis. Speed on the y is going to be different. We're just saying that for now, because they're not really going to be different. They're going to equal the same, but we're just saying that for now. So in essence, we're saying that the mean square speed, right, along the x-axis is equal to the mean square speed on the y-axis is equal to the mean square speed on the z-axis. Now, all of this right here is really equal to the average mean square speed that we just showed you in the equation, right? So this thing right here that says mean square speed, all of that is really equal to the sum of the mean square speed on the x-axis, on the y-axis, and on the z-axis, right? But since we know that the mean square speed on the x-axis is equal to the mean square speed on the z-axis, and equal to the mean square speed on the y-axis, then I can just say that all of these things right here are the same, so we can add them up. When we add them up, we end up getting 3 times the mean square speed for the x-axis, right, being equal to the mean square speed in general, right? So that mean square speed is a very large thing that it speaks about, right? It speaks about the entire speed that all particles would possess, so to speak. But because we're saying that all of the speeds are the same, I could go ahead and just pretty much add them together, right? Since all of them are equal, so I would end up getting 3 of my mean square speed for my x-axis, because it's obviously the same if it was on the y-axis or on the z-axis. And with all of that being said, right, we come to this point. We are now at this junction where we are now saying that the mean square speed on the x-axis is equal to 1/3 of the mean square speed in general. It's a lot of information. It's a lot of crazy stuff going on. But I don't know if you guys see what's going on here. If you want to say something, go ahead and feel free to say something. Now the question is, if you were to replicate most of what is going on here, do you guys think you'll be able to can do so? All right. So Rihanna said I should explain again from therefore. All right. Let me go back to that point. Okay. All right. So from this scenario, we're saying that all the pressures are equal to each other, whether it being on the x-axis or whether it being on the z-axis or the y-axis. Doesn't matter. All of them are equal. Now, the number of particles on the x-axis is equal to the number of particles on the y-axis, and is equal to the number of particles on the z-axis. So basically, because there are three, uh, I'm trying to understand what you're saying earlier, all right? But I soon come back down to that part where you'll see it again. So this n right here will cancel because they're obviously common on both sides, right? So we're equating all of these three things. The mass is the same, the volume is the same. So we're canceling out all of these things, right? Then we're left with the mean square speed on the x-axis. We're now saying that that is equal to the mean square speed on the z-axis, and it's also equal to the mean square speed on the y-axis, which is what we have at the therefore scenario, right, where we could have seen that all of these things would have canceled out. Let me see what she's saying. So therefore, if we have four, well, we don't really have four axes, but yes, that's what you would have had. You would have basically produced if you had four axes. Yeah, right? But we don't have that. Yeah, man. Right? So because we're saying that um, the root or the mean square speed along the x-axis is equal to the mean square speed on the y-axis is equal to the mean square speed on the z-axis, right? In essence, we're saying that all of these three things, they are equal to the same. So if I go ahead and say 3, right, times any one of them, which is, I'm going to use the mean square speed for the x-axis, right, that would equal to, that would talk about everything here because everything is equal to the same. If I had y, it wouldn't affect the price of rice because we're saying that the root or the mean square speed for the y-axis is still equal to the root. I'm saying the wrong thing. More I can't talk about this. I hate to talk about this, right? Um, it's equal to the mean square speed for the z-axis is equal to the mean square speed for the x-axis. So all of them are equal. So I could just collectively say 3 times the mean square speed for the x-axis, which is what we did right here. But before we reach to that point, because we are involved in 3 axes, right, or 3 axes, right, then it means that our mean speed would be a sum of those, right? It would be a sum of those and divide that by 3. I believe it will be divided by 3. Let me see here. Give me a second. Yeah, it will be. I think it should be dividing by 3. So really and truly, our mean square speed is the sum of all of these, dividing that by 3, right? Let me just check here. If I divide that by 3, if I bring this across, uh, okay. Well, no, we're not saying that. Let's not say that. Let's not say that. We're not going to say that it is the sum of these and divide by 3. We're not going to say that. Let's not say that, because if we say that, we're going to run into problems, right? We have already established what the mean square speed is already from day one, when we had u1 square plus u2 square and all of that. So we don't need to go back to that realm again to divide it by anything. We just need to just add up all of these right here to tell you what the overall mean square is equal to, which we are now saying that that is equal to the mean square, right, is equal to 3 times the mean square of the x-axis, right? And by just transposing the equation, I'm going to transpose to make the mean square for the x-axis becomes the subject, as you're seeing right here. All I would have done is to just divide this side by 3. When I divide that side by 3, I'm now left with the mean square speed for the x-axis, right, equal to 1/3 of the overall mean square speed. If we look back around here, so we were at this point to say that the total pressure along the x-axis is given as this. So what we're going to do now is to take into consideration the total pressure. Perfect. Now we're going to take into account the total pressure, because this pressure was the pressure for the x-axis only. But now we want to consider the total pressure on all the axes, basically. And for that reason now, we're going to basically substitute, right? So just a while ago, we found out that the mean square speed, right, for the x-axis was 1/3 of this, right? So by way of just substituting that into that equation here that says P is equal to Nm, right, divided, not divided, but times by the mean square speed. And when we do this now, if we make that substitution, our total pressure, right, on the, I would say the total pressure on the x-axis, if I'm correct, I think it will be the total pressure on the x-axis would be equal to N times M divided by V, right? Let's put it 1/3 in front, and then now times that by the root mean, whatever that thing is, the mean squared speed. So this right here makes the very first major equation that we need to know as it pertains to these things, right? This is the major equation, as you can see here. I think you guys have the PowerPoint already too. So that's the major equation that we just derived a while ago, right? That just simply tells us that the total pressure, right? And I'm assuming here that this is the total pressure for the x-axis. I'm just assuming, because if we just substitute that the mean square speed for the x-axis to be 1/3 by the average or the mean square speed overall, then I think this pressure here is just talking about the total pressure on that axis. I'm assuming, right? But remember, we said that that pressure is equal to the total pressure. Well, that pressure is the same pressure that will be exerted on the y-axis and also on the z-axis. So once you know one pressure on one axis, then it counts for all the other axes, as you would have seen right here, because all of these pressures, they are equal to equal the same, right? They're pretty much equal. But there's a second equation that we can bring into being here. And if you check your syllabus, you will see it in it as well, right? And this is the second equation right here that says P is equal to 1/3, right, times the density, good, times the mean square speed. So this is another equation that you can be asked from time to time to use to find the pressure, providing that you know the density, providing that you know the mean square speed, pretty much. How did we get this equation? We got this equation by way of looking at this first equation that we looked at, right? And when we're looking at the equation, I'm seeing mass divided by volume. We know that mass divided by volume is density, right? But in this case, there's an n being multiplied right here. This n speaks to the number of molecules. So if we're talking about all of the pressure that is being exerted on the walls, right? Then we have to take into account all of those particles. We can't just single out one particle and talk about that density. So for this now, we have to multiply the number of particles by mass over volume, because that now we talk about that total density for all of the particles that are basically adding up to make that overall pressure. We can't just single it out to just one particle, if you get what I mean. Let me know, guys. Right? I mean, it's really a lot of stuff. Give me some comments. Let me hear what you guys have to say here. Learning this part of it is not the easiest. We're required to remember these equations. Even if you don't even remember the proof, you have to find a way to remember the equations them that we're looking at here. There's no easy way of remembering them, right? But I mean, it's just a matter of you sitting down and taking maybe a few hours to say, all right, let me go back over this and see what's going on here and all of that, right? Because as I say, it can be something that can come on the test. Who knows, right? But we must know at least the equations that we're looking at. Yes, yes, we are considering all the particles, right? In this regard, we're considering all the particles because all of those particles are what are adding up to give you that total pressure, right? So when we try to find that density now, we can't just single out one mass of the particle. We have to take into account all the masses, which would be multiplying that by the number of molecules, because they would have the same mass basically. So you just multiply that by m, divide that by the volume, and you call it a day to find that get this equation that says pressure is equal to 1/3, right, times density times the mean square speed. Right now I don't have any questions, but I see. Okay, yeah, well, no problem. As long as you will do that eventually. Because there are some people who might not sit down and even try to think about it, right? But yeah, sure, no problem. But at least make note of the equations that we have on the screen, though. All right, so we're kind of moving on now, right, to other equations that we are tasked to talk about. One equation here is that we're going to basically derive is the total kinetic energy, right, of a monochromatic gas. Anybody knows what a monochromatic gas is? For let me know if you know what a monochromatic gas looks like or what it is. If you want to give me examples, no problem with that. But let me know. By the way, I think there's something I want you guys to document here, and it is this information because it sometimes comes into play. Um, and they can even ask you about this, right? It's what we call the root mean squared velocity, the RMS value, basically, right? The root mean squared velocity is the square root of the mean squared or the mean squares of velocity of an individual gas molecule, right? It's just a definition that they can sometimes ask you for, right? I soon show you what it looks like in terms of um, how you go about writing it. But this is what we call a root. There's something we call a root. So when you hear me mix up the terms, a root, something like that, is because I'm familiar with this, right? So this is what we call a root mean um, squared velocity. In some case, we call it the RMS voltage, or not voltage. In unit 2, you hear we talk about RMS voltage, but here we're talking about the RMS velocity, right? And it is just the square root of the mean square speed of velocity of an individual molecule. So you can just write down that definition somewhere in your book, right? I think the root mean square velocity, right? Kind of helps us in finding what is the individual speed of the particles. You see what I mean? I think that's the essence of it, right? I think that's the essence of it. All right. I think you have that written down now. All right. Let's look at what it generally how we go about writing it mainly. I mean, I think we can reach to the point where we can find out the root mean square speed or root mean square. Yeah. That's that thing. We soon reach that point where we can pretty much calculate it, right? But I mean, when you look at this right here, this is pretty much you finding the the RMS velocity, right? That is you now taking the square root sign and find and just square rooting the mean square speed, right? So once you do this, then you will find the root mean squared velocity for an individual particle, right? Well, we'll soon get to that a little bit more. Let's see what's going on here for the kinetic energy. So they want us to derive an equation for the total kinetic energy of a monochromatic gas. Now, I still pose a question to you. What do you think is a monochromatic gas? I know I have chemistry students in the class, right? You have a good chemistry teacher. So tell me now, what is monochromatic gas? All right. So one person said gas with only one molecule, with only one atom. You want to expound a little bit? Also, you just guess. All right, no problem. Um, that doesn't have to do with things such as noble gas. Yeah, you have a right. Yeah, that's right. Gas in which the atoms are not bound together. They exist as a single atom. Mm, not quite. But what I must say to you guys is that any gas that you hear about, right? They always exist um together, right? Which that is why gases. Anywhere you see gases in chemistry, you will see some either H2, right, or you will see some uh I don't remember O2, right? Because those gases does not exist by themselves. They have to pair themselves with one another for them to be classified as gases, right? You can't have one oxygen and think that that oxygen is just a gas. It has to bond with another oxygen for it to become an oxygen gas, right? So that is kind of like what we call a monochromatic gas, meaning that it only consists of one atom, but it's a molecule of itself, right? So let's just look at it quickly here. So yes, it's one single atom that makes up the gas, but it is bond with another monochromatic. Is it mono? What did I say about it? Monoatomic, right? So what's her name again? Carries what I've said. The noble gases, of course, the noble gases would be classified as monochromatic gases, all right? They will be classified as monochromatic gases. They exist in pairs and they are just by themselves, you know, right? Let me check something here. Let's just look at it again. So we want to derive that equation, right? Of the average kinetic energy of a monoatomic gas. So for us to do this, we have to consider the equation that we just derived a while ago for the pressure, right? Um, you know, so let's look at it here. So we start out with this equation that says P is equal to 1/3 of N times M divided by the volume times the mean square speed. It says that relates to a macroscopic property, pressure to several microscopic particles, which is what we call the number of molecules, mass of the molecules, and the speed of the molecules. It says let us now compare this equation um, with the equation of state of an ideal gas. So we're going to compare those equations. Sir, what is N in the equation again? N is the number of molecules, But this small n now is going to mean the number of moles. So this n is the number of molecules, and this one is the number of moles. Okay. Now we're going to compare the equations. And for us to compare them, we want this equation here. Come on, thing. We want this equation to basically look almost like this equation. So what we would do is to just rearrange it. When you rearrange that equation, we get that P times V is equal to 1/3 of N times M times the mean square speed. As you can see, we can compare the equations now because we have PV here, so, and we have PV in the other equation. So this is the first equation, this is the second equation. We can compare them now. When you compare them, you're essentially equating them to each other, right? So nRT is going to be equal to 1/3, right, of Nm times the root mean squared. All right. So we have that. That's us comparing the equations. That's the first thing you generally do by way of starting out this proof that we want to come up with. Right? We're going to see the works of it coming down the line. If you're taking notes or anything of that nature, just let me know so that I can give you 1 or 2 minutes to do that. Then we just jump over to the next part. All right, good. Yeah. So what does R represent again, guys? Anybody remembers what R represents?
So the molar gas constant.
Yes, the molar gas constant, and I think that value is given to you. Molar gas constant. I think
Yes,
it's
sir.
8.31, I believe. And by the way, just ensure that your temperature, if you're going to work questions of this nature, it has to be in kelvins. All right. So that capital T is basically talking about temperature in kelvins. All right. This thing here is going to be a little bit not say tricky, but we're going to do some crazy stuff here very soon, right? Some mathematics kind of thing, because what we want to do is to get an equation that says we know the equation for kinetic energy from day one is a half mv squared, right? That doesn't change, a half mv squared. So when you go over to the next slide, you'll see us doing some stuff because we want to see a half mv squared in the equation, but not necessarily a half mv squared. We want to see at least a half m times the root, not the root, but the mean square speed, basically, right? So that's what we want to get at, so to speak. All right. So I think I can next it now. All right. So this is the overall equation that we want to get at. That says the kinetic energy, EK, is equal to 2/3, right, times N times R times temperature divided by N. So we equated the equation. When we equate the equation, we get this. All right, we get a third times N times M times the mean square speed, good, being equal to nRT. What we're going to do here, right? In mathematics, there are times when we can do things to equation to just get it to a particular level where we want it, but it does not affect the overall answer. Because if you do one thing to one side and this next thing to the next side, change the price of rice. You only do it because you want to manipulate the thing so much so that it gives you what you want. And this is what is going to happen here. If we take both sides of the equation, remember at the end of the day, we're looking for kinetic energy. And kinetic energy says a half mv squared, right? So we are looking for that. We want that. That's what we want. So we're going to know times both sides by 3 over 2. So if I times both sides, so this is 3 times 1, 3 over 1/3 times n times m times the mean square speed, right, being equal to nRT. If I multiply both sides by 2 upon 3, on this side, 3 divided by 3 is going to cancel out, now leaving me with a half n times the mean square speed equals to 3 upon 2 nRT. I'm seeing a half mv squared or half c whatsoever that thing, not half mv squared, but mean square speed. I'm seeing that. That in itself speaks to kinetic energy. So I could simply say Ke, or Ek for argument's sake, times n, right, is equal to 3 upon 2 n times r times t. Then I don't want this n on this side, so I need to just divide both sides by n. Now, simply put, I now got the equation that says the kinetic energy, right, Ke or Ek, you know you want to call it, is equal to 2/3, right, times n, which is the number of moles, times the molar constant, times the temperature divided by the number of moles, right, gives me this equation for finding the kinetic energy, right, for a single molecule, right, of a monochromatic gas, right? So that is just the equation there. It's not a hard proof. This is a general proof that you can see on a not multiple choice, my bad, on a regular paper, because this does not require a whole lot of working out. You would have just required to know the two equations you'd have required to know. You'd have required to know the one that says P, right? PV is equal to 1/3 times n times m times the mean square speed. And you'd obviously need to know the general or the ideal gas equation that says PV is equal to nRT. Now, guys, you can't forget, when you're doing module 3, you can't forget none of these equations, especially the foundation equation, the general or the ideal gas equation that says PV is equal to nRT. It's something that you have to repetitive, you have to say it over and over to remember it, right? PV is equal to nRT, and you can derive other equations from it, right? So don't forget them. Do not forget them. This one as well for kinetic energy. Don't forget it either. Remember how to prove them. If you remember how to prove them, then you can't go wrong in the exam. All right?
Sir,
Yeah, go ahead, please.
the common n is the number of moles and the capital is the number of molecules.
Exactly, right? So small n is number of moles. Right? And then now big N is the number of molecules. And sometimes too they ask you to define these things. Not to define them, but to tell us what the symbols mean. So like N, small n, number of moles, big N, number of molecules. And they could ask you, what does this mean? The mean square speed, right? They can ask you these crazy things. Mean square speed, right? I don't know how much of this they're asking again, these easy questions, but they can ask you these things, guys. And if you check the narrative of your past papers, you'll see the general format or the general structure of the questions, and you'll see these things coming out. All right. I think I can move on now. Sometime in physics, we're going to do some stuff to equations to just make it give us something that we want. You understand? Sometimes we're going to do those things. And this is not the first and the last time you're going to see us doing these type of manipulation, right, to get what we want. Because we wanted to prove the whole kinetic energy. And we know from day one that kinetic energy is equal to a half mv squared, right? So there has to be something that we have to, do in order to get that. And from a mathematics standpoint, the best thing for me to do is to times both sides by 2 divided by 3. Once you do that on both sides, you're going to see the 3's canceling out. You understand? Because if you times 3 upon 2 by 1/3, then the 3's would cancel out by cross multiplying, leaving you with a half times n times m times the mean square speed being equal to 2/3 by n times rt, right? This is the equation now that we can manipulate to find the what we call the root mean squared. This is the equation that we can use to find the root mean squared, right, of the molecule. So we could transpose this equation to find the root mean squared, of course, right? Obviously, you would have to let me see if we make mention of it around here. Not yet. Let me see. So let me just write this around here to show you what we mean. So if we know that the kinetic energy is equal to half m times the mean square speed, right, being equal to 2/3 times n times rt divided by n, right? Then I can now manipulate the equation so much so that I find the root mean squared. So clearly, I want to find the root mean squared. So I would need to get rid of all of these things that are here, right? So this 2 is gonna come over here. Let me just do that quickly. So is equal to times m times rt divided by n. We're gonna times that 2 here, so we're gonna divide by m, right? We know that these 2's and these 2 cancel out, right? If we square root the answer, if we square root the answer, you see, by square rooting the answer, which is 3nrt divided by n times m, this will tell us the root mean squared. The root mean squared, right? This will tell us the root mean squared of the particle. So the root mean squared velocity, right, can be found by just square rooting this answer right here, right? In some case, you will see us write Vrms, right? Or we could essentially use this symbol to say the square root of the mean square speed is what we call the Rms velocity. Let me just clarify and verify that.